Hello class, in this lecture we study about flip-flop. Flip-flop is nothing like a switch. I flip it on, it stays on. If I flip it off, it stays off. So it's nothing but a single bit of memory. If I set it, it stays set. If I reset it, that's reset. In other words, a flip-flop is like memory stick is like a matrix. Each switch, if I have a matrix of switches, I can keep them on or off. For example, I want to store the number 1001. So the first switch is on, second switch is off, third switch is off, fourth switch is on. So it's one, on, off, on. So if I want to store it and I leave it there, come back and I want to remember what number was stored, I look at the switch position, it's on, off, 101. Such a process of using switches, latches. Why is it called a latch? It stays in the same position. If I latch it on, it stays on. If I latch it off, it stays off. So understanding a latch is like how a switch works. Now to understand it, this is what makes up memory, what makes up RAM, your ROM, how data is read from how it all works. Understand basic fundamental. Yes. Now let's look at it. The way it has developed over. So this is our syllabus. We're going to talk about flip-flops, RS flip-flop, D flip-flop, toggle, which is put to toggle between states, Jakey flip-flop, master slave flip-flop, clocked flip-flop, trigger leveled, edge trigger. In other words, it's a leading edge or lagging edge applications. So let's go into this. Flops are an extension of what we saw earlier with logic gates extension. So it's a logic gate, sequential. So you have an input, output. There's an output that feeds back into the circuit. Help it hold the state, same state it was earlier. So be able to remember what value it was set with. Now let's look at it. So the first flip-flop we're going to look at is called the SR flip-flop. Set, flip-flop. Now you're going to be realizing this with the gate we talked about as the universal gate, the NAND gate. Okay, what happens? A flip-flop, if I say S was high and R is low, even if the S goes low, we'll remember that state value Q, which is your output. And what is Q dash? Inverse of Q, but with inverted output. So depends now. If I want to remember the inverse, I use Q dash. If I want the Q, now let's look at it. State. So when I have S goes high, R goes high, what happens in these different states is going to be studied with the truth table. Let's look at the simple truth table. Now, a positive NAND SR flip-flop. Now let's look at this. When both the pins are low, inputs S and R are low, the output has no change, which means it remembers the previous state. Yes, it has no change. For example, R goes high and S is low, output low, and Q dash is high. If S is high and R is low, Q goes high and R goes low. In other words, when I say set, it flips on. When I say reset is triggered, it flips off. So this is reset pin, Q is off. Set pin is high, Q is on. Both are on. It's not an invalid. It's an invalid condition. Not consider this, but it can flip it on. In other words, I use to. Let's go back and look at our switch to understand it better. If I have my set as my input, I hit the set, the switch is on state, I'll leave it there. In other words, my input is not there. So this is my set position, this is my reset position. When I hit set, it's set. I hit reset, it's reset. So looking at the state is only when I set it, it's set. After that, any more type of set is still set. If I hit reset, it goes to reset. Any more reset stays at reset. So set position, reset position are two different inputs. In other words, set can't trigger a reset. So how is this happening? I have two outputs, a flipped input, output Q, sorry, flipped output Q dash and my output Q. This is what is being considered as my state outputs of the flip-flop. Now this is how it can be realized as using gates. Now this is one such flip, okay, called SR flip-flop. Now I can realize there are drawbacks with it. In other words, when does it change state? I don't have control over it. I want it to change state only when I tell it to. So that's the development of a JK flip-flop. In other words, if you look at it, it's actually an SR flip-flop on the end. Now, I also have a clock input. What is a clock input? It's the same JK flip-flop, I mean it's SR flip-flop, but now when I have a clock input, I tell you when to change states. I can have J high, K high, or J low, K low, it doesn't matter. Only when the clock comes in, the edge of the clock comes in, when the clock goes from low to high, that's when the state changes. Other than that, there's no control. I mean, in other words, clock controls when the state changes. So it is the same flip-flop. J comes as an input, K comes as an input. Only when the clock gives a trigger, that reflects in the output. Other than that, there's no change in the design of the circuit. So in other words, I have a flip-flop whose output I have control over. I tell you when to switch. So clock, the master control. In other words, the same as SR flip-flop, the toggle action is controlled by the clock. Yes. So you have the no change, which is the memory form. It remembers the previous state. It's reset when Q goes low. It's set when Q goes high, and it's controlled by the clock. So clock controls the change state. Other than that, it stays in the previous state. No change, which is your memory condition. So in other words, SR flip-flop where I control when there's a change of state. So there are different manufacturers with different options and different configuration set. Each device IC has a name standard. So in other words, I can get flip-flops inside an IC. I have two flip-flops in this side closed. Case it's a yes. Let's look at the next flip-flop. Call the okay. So the D flip. I have only one. In other words, I have data coming, and I want to have the data stored. So I have a gated. When I say gated, it's a clock control gated SR flip flop, and the input. I mean, in other words, the data that's coming is also inverted, and that's what control is. It's like a gated in. So the block diagram is a input, clock input. And now what happens? Logic truth table. Now, memory status doesn't matter what D is. And if my clock goes low, 0, memory stays whatever was previous. The clock goes high, and D is my input low, records low as my output. Q dash is the inverted output, so this is Q dash. That's the inverted output of 0, which is 1. And in case I put my input D as 1 high, and when my clock goes high, remembers, it sets it as 1. In other words, same thing, but I have control of data coming through the input, and my output changes state, control clock. And when the clock goes low, whatever value was there earlier, it was high or low, based on the value of D earlier, when the clock was high, that value stays there. As long as the clock is low, data, if it was high, it stays high. So next clock input, next data line comes. So is it complicated circuit? No, it's a simple circuit realized with NAND gates. And what happens is, simulated, you'd understand that it helps remember one bit of data. If I say it's on, it stays on. If I stay off, in other words, I can use it to store one bit of data. So I'll have an IC, another 14-pin IC, pops inside it. The complicated. See its application a little later, but let's understand it with its fundamentals. Let's look at a circuit. We talked about a flip-flop. When I give the clock input, change state. So I set D high or low, and I give a clock input. Remember that state. So this is Q dash. If I keep D as low and give my clock input, it will remember that as low, but Q dash should be high. If I keep it high and give a clock input, it set Q as high, Q dash should be low. This is a working circuit with just a simple understanding of how clock input controls the output. Okay, let's look at it application. Now, talking about our quartz crystal, talked about the frequency of the clock crystal. Let's go back and look broken down. Yes. So this precisely takes 1 second. What happens? Why does it take it? This is because it has a crystal oscillator inside, which is oscillating at 1000 sound. Now I need to bring down that frequency 32,000 sound 68 second, which 32,000 sound 68 divided by half comes down again, and again it divided by half. I have to divide it by half 50 times. Now, such an application, I need to reduce it in half. Done. In other words, I use JK flip flops in this, cascade them. I give an input clock pulse. This input set high. These inputs, this frequency, we tap it here, clock input pulse. Whatever I give it here, this is followed. Since this controls the next phase, this output connected to the clock input. In other words, only when this comes high, this clock change state. Control the output to change state. In other words, if this frequency is 32,768, it should be half the frequency. So flip flops do have an application. Now, if I do this 15 times, half again, the output frequency is 32,768 hertz. 15th time, 1 precisely. If this was precisely 32,760, the output would be precisely 1 second. That's how clocks exactly think. Have you seen these scrolling LED boards? In example, you look at the alphabet. In other words, if I have text come up on the first segment of the, I'll try to see if I can video of that. It whatever is there, and I'll try to show you. I'll explain it first. Let's like look at the theory. A ring counter is I have the values inside the counter, yes, and if I give a clock input, which is a particular value, in other words, it pushes the data to the next register as it once data when I give the clock input, next phase. So whatever is there, it keeps pushing next, like shifting it, like another person comes in, the person in the queue moves forward. So whatever data is there, it's shifting. It's called a shift register or a ring count. Okay, so it's a ring count. In other words, what goes to the end, back. So it's a ring count. For example, where is the application? Practical. Have you seen the serial lights when you have three LEDs driven by three LEDs, three outputs driven your photo frame? The lights going around. The truth is, the light is not moving. You have three sets of LEDs. Set number one is on, and it goes off. Set number two is on. For I expect to say that okay, set number one is on. You think all the ones are on, and set two is on. I trick to say that two is on. So what is this IC inside? It's actually shift register, a ring counter. So it goes to 1, 2, 3, 1, 2, 3, 1, 2. This sequence is like a three-phase power supply. The only difference is that there's only one on at a given point of time. Only one on at a given point of time. It's either on, either off. Why do I have this transistor? So that this small ring counter can't handle the heavy load required to drive an LED. This will be operating on high voltage. So this is an IC called the 555 IC. IC used to generate a square wave, timed, precise timed wave. So that's the IC required to drive. So this has a resistor and a capacitor required to get the required timing required for the IC to operate. And this output is given to this counter. So once the count is coming, it's like pulse on and off. The first pulse goes to the first output, second pulse goes here, third pulse goes here. In other words, what is happening here is this counter shifting that back in circles. Truth is, this IC can handle a lot more output. Okay, let's look at it. Practical experience. So what does this circuit do? Shifts output, next stage, whatever was input, it shifts this output to the next state. So in other words, if I have the lights, if I have 1 and 2 on, and when I shift it, 2 and 3 goes on. So in other words, it's just a simple counter that you probably see all the time with lights flickering around. So let's look at another one. Yes. Now, what pattern should I move around? It's like 1 bit moving around, or if I have 2 bits moving around, or 3 bits moving around. This pattern is practically possible with this particular circuit, the Johnson um, encounter. In other words, I give my data in parallelly into the system, and it can give me the output parallel. In other words, whatever goes into the system keeps shifting, yes, goes around in circles, but output I can read it parallelly. So at any point of time, I can see the outputs. I can see all 4 of the outputs, but the data that comes in goes serially. In other words, I say on, there's a clock coming in, the logic coming. In other words, I keep it high, set the clock, high goes here. I keep it off, I give the clock, 1 goes here, 0 that was low, that's a 0 here. So whatever comes in as serially goes out parallelly. In other words, I can move the values. I can say if I want to put the value 0 1 0 1, I put 0, put the clock, 0 is here. Then I put a 1, I click the clock, this 0 goes here, 1 stays here. Then I again make a 0, then the 0 goes here, there's a 1 here, there's a 0 here. Again I make it high, 0 here, 1 here, 0 here, a 1 here. Now potential ring counter. In other words, it goes around in circles. This ring counter and this process of sequencing it out can be read parallelly. So let's look at them in with the practical expression with maybe an animated session. Maybe a video I could show you from then. But this is a first concept of understanding what happens. Johnson. Another application of subplot. In other words, are the lights keep flickering, pattern of flickering, control clock, and that's use of your D of Johnson. So, get it from my standpoint. In other words, I want to have data. Now, when I say I want to store data, I want to have data in serial in, parallel out, serial in, serial out, parallel in, serial out, parallel in, parallel. In other words, if I have 4 data lines to write data, put all, example, the pattern is 1010, I can give all data in as serially in 1010 coming in with the clock pulse timing it and going out parallelly. Or I can send it out serially, like what we saw on the Johnson's counter. It comes out, it goes serial in, it comes out parallel, like what we saw on the Johnson counter. But in this case, I can also have it serial in, serial out, or I can have it parallel in all 4 lines, parallel input, but I can read it out serially, or I can have all parallel in, parallel out with same. So data comes in parallel, data goes out parallel. I can hold the data I have of. Yes. So what controls it? The clock. If I have the data 1010 here, if you want to clear it, make it all zeros, you have a clear line. Yes. And what comes in through serial data? I can read it out. So what's happening here? The data is being shifted, process. But this is so we would understand its operation. So you see the value shift, one goes keeps moving. Next pin. Instead of moving, data moves from one every time the clock pulse moves, it moves. So this is how data is being transferred. I mean, you can use it to transfer data serially in memory or parallelly. So this is all it can be applicated. It can be an application like how we talked about lights flickering. You can read the data in that case. At the same time, it's also used on the data parallel. Parallel. So this is the simplest understanding what a shift. Let's look at it another way also, and with straightforward. So this is another way of looking at the ring count. Okay, so back to next topic, which is What is a decay? So I should be able to count, and I want to do a mathematical operation. Such having mathematical operations done with simple, I should be able to count with binary numbers and understand how it can. So I have a set of LEDs expressing binary number, and the outputs in this might be like a bar graph, and I want to be able to have data stored in it and be able to out and have it uh, counted. I want to count. I want to count to 10, and give me an output when it's 10. Such an operation done with such. So is it a is it a simple concept? So you have your input coming in. I'd be able to get a precise. I talked about frequency dividers, like how you can get half of it. So when you get the 10th input, you want to get the output right. So you can count to a precise number. Such a configuration of counting possible with digital electronics. And I can have it visually visible in case I have the circuit where I can have LEDs count up for me. Okay, I'll try to see if I can animate it for you and show you working of concepts, practical session. And I said exact IC that we have in our. Okay, this the reason I'm showing you this particular concept is because I have this particular IC that's on. So this is the IC we talked about. It can count all the way up to 10. In this case, it's counting 1, 2, 3, and back to. So this is the exact circuit, but in this case, instead of having 3 outputs, I've realized a circuit where we can have 10 different. Yeah, this is what the IC is capable of doing. Showed you a smaller version of it. I can express it to help you understand it. Now let's look at this particular animation. Now this is, let's look at a flip. Look at an SR flip. Okay. Now in this case, this flip flop has a clock input. Clock input keeps toggling between high and low. Now my inputs are here S and R, set and they're low. So what controls the output? Now it remembers the previous state was. So this is the outputs and this is the. Now this is realized with using AND gate. So I can switch this. I can, if I set it and if I set this high or low, control the output. Remember the state. Though the clock changes, remember state based on the input. So low. Now in a similar way, let's realize another circuit. Take K. Now I have inputs here. K input, the K input, the I output. What is controlling it? Clock pulse. So you can see how this logic circuit works. In other words, if this is inverted, if the input is high, output is low. If the output is high, you can see each gate working. So this is an AND gate with the 3 input NAND gates. Input AND gate. You can see control of how each line works and how this feedback loop works. You remember the SR crossover latch concepts here. Now it's real animated. So I can change these states and remember the state, and I can. So the edge triggering in this case, now we'll look at a D flip flop. Edge, in other words, when you say clock pulse, when the clock goes to high and low, talking about edge trigger, is how we can have this. Let's see the state change animated. So your input is made low, output is low, non-inverted up, in your regular output, inverted up. And the clock keeps ticking. So when I keep it low, low. My data goes high, change the state, high. So this is a simple edge triggered. In other words, when does it change state? Only when the clock changes state low to high. That's when the output Other than that, there's no output for it. Okay, so let's look at master slave. So when you say master slave, it's a cascaded option where you have two sets of, in other words, the master control application. Let's look at it in logic real how it works. Your input is high, clock is toggling state, and output is high. When input is at low, clock input, change the state, output. Now again it's made high, output goes high, goes the same state. I flip it again low. This you can see the logical circuit used realized with not gate NAND gates expressed. So this is a simple example of how you can express how a change of state of your input can be stored as one bit of memory. Have the output change states only when clock. So you this is operating on a simple 5 volt expression. So you have low is 0 volt, high is 5 volt. The flop change state. Usual gate, usual logic gates who operate in circuit able to realize. So what's the difference? Now I have a pen drive. I store data onto it. It remembers it longer time. Hypermemory is memory which is electrically erasable and programmable, and remembers its state because it's once I flip a particular value in it and the data is stored. So this type of memory is this ROM actually. So I can read its state, can also electrically program it. So talking about state changes in this ladder logic based on the availability of power does not. So it's more of RAM. So it's random access. You can read the data, see the state change, whatever is there, you can read it. But the power is gone. But in this case, first is kind of permanent. So when you format it, you reset it, you do control the reset line and you reset it back all to zeros, data in it. So when you write data into it, you flip those switches on or off, and the pattern is remembered and read the data at any point of years later. So from a pen drive that stores memory to a sequential circuit that has an LED going between 1, 2, 3, and 1, it all works with a simple concept of understanding how one bit of data can be stored, memory, able to that output. So you have flip-flops here, yes. You have a counter that can divide your seconds frequency from 32,768 down to 1 second. Works with the same concept of frequency. So all this fundamentals required to understand digital electronics. So digital electronics is just beginning. In you working with these such ICs is just the beginning of understanding what the bigger picture is, how you can apply a simple concept to be able to realize a bigger circuit. Now let's get another interest. I have digital data, but I have to display it on display. This input could be binary numbers. I have numbers 00011. Now 00 should represent the number 0, 01 should express the number 1, 10 should express the number 2, 11 should express the that's with data. I can go 0, 1, 2. I have 4 combinations. That's numbers I can count with just 2 bits of data. I can count all the way until 4. Now converting this binary number into decimal number base 10 possible. You look at that. Okay, binary. In other words, when I have a binary number, for example, in this case, switches have the value 0. It's all off. have the values. I can go from 0000, have all these four switches to 1 1. Talking about 4 bits of data. Now, using this 4 bits of data, I'll be able to see if I can count or display the appropriate value. If it's going to have going to be off, 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 I should have the segments A, F on say the number. So these are the segments of your LCD earlier. Yes. Now let's see if we can have this realized with a realistic circuit. Let's look at this video to see how it can be realized. So when you have this connected, so you have the power supply connected to the segment. You're going to have each segment, each input from your output of the BCD converter, A to A, B to, because this BCD IC has all the pins required to drive your 7 LED right on your segment. You drive it, when you turn it on, for example, all the four switch off, place the number 0 on it. Now, if I toggle those switches, all four set, I can have it 1, or I can make 2, or keep both on, that will become 3. I want to make 4, 1 switch, that's 4. 4 plus 1, 5. Fourth position, 6, 7, all on. Last bit is 8 on, center segment will turn on. So using simple IC, I was able to get. So using the simple IC, we were able to count from all the way from 0 to 8, 9, and 10. So all since we had only 8 bits, then the last switch is on. For example, I have the fourth switch. I switch the fourth switch on and 3 off. Display 8, 8 first bit, 8 plus 1, 9, then 8. I make 1, 0, 1, 0, 9, 10. So that will be 0 again because it have output shift, have your the last bit carry over counter shift 0. So now you can count using a simple BCD converter, which will help you to convert your values from 0000 1111 control a 7 segment display. This is what 7 segment control. So when you start talking about binary coded decimal, I would be looking at A, B, C, F. All those segments as zeros and ones be able to express the number 0, 1, 2, 3, 4, 5, 6, 7, 8. Now let's look at it in a different aspect of how it can be realized with logic gate. So this is circuit. This is the IC that we saw. Let's look at the internals of the IC. So okay, it's logic. You have your 2 input, 3 AND gates. You have your inverted OR gates, inverters. So these are the 7 segments we talked about. 7 segments of the IC. The LED is a 7 segment display. F, G. Have those 7 outputs are your in. Have the 4 inputs 0, 0, 0, 1, 1, 0, 1, 1 all the way. So you're talking about 0, 0, 1. First bit is so it's 1 from all the way from 0, 0, 0, 0 to 1, 1, 1, 1. Look at those sequence also and see how this sequence converted to control exactly the right number of segments on your 7 segment display. Have that particular segment light up. Example, you scientific calculator. I press the number 1, lights up the number. I mean, it displays the number 1. How does it know to light up the right LCD segment or LED segment? It's what is happening. Calculator. Example from your weighing machine. This is what is there. Your B 7 segment. Yes. So let's look at the truth table to understand it better. Now let's look at table of. So these are the segments, 7 segments, 0 to 6. Okay, and this is the input, so the 4 switches. Now we talked about 0, 0, 0, middle 1. But your 7 segment display can display 10 digits with 0 to 9, single 7 segment. Now let's look at it, how it does it. Now, this is all done by the circuit I showed. One by R4. Now look at this. 4 inputs should result in all the outer segment on segment. So all on circuit. So this control of giving this 4 input 0 0 0 0 to control all these bits from 0 to 5, display the number 0, done, convert. If I have the one number 1, the binary number for 1 is 1, for 2 is also this is 2, 4, sorry, 1, 2, 4, 8. Remember the numbers 1, 2, 8. These are the numbers I have in my BC binary to convert it into this. If I want the number 1, I pick 1. If I want 2, I take 2. If I want 3, it's 2 plus 1. So it's 4, it's 4. If I want 5, 4 plus 1 is 5. If I want 6, 4 plus 2, 6, 7, 4 plus 2 plus 1 is 7. 8, 8. So this is how I look at this. Now it is 1, 2, 2 plus 1 is 4, 4 plus 1 is 5, 4 plus 2 is 6, 4 plus 2 plus 1 is 7, 8 is segment number 8, 9 is segment number 9, 8 plus 1, 9. So when I have the number 8 displayed, all the segments are on to display. I have the 9 displayed. This is sliced by IC logic gates. So this is a circuit again. So when I gave my inputs 0 0 0 0, this logic work output operate exact 6 segments 0, or if it's for all ones, only the fourth bit is 1 8, all the segments turn on to display. So this is a great achievement done by our forefathers to have logic able to display a number. And now these days it's all, and by the way, these logic gates are designed with transistors. So if you remember talking about an inverter, how a transistor can be used as an inverter, high and a low can be used. Now imagine the number of transistors required to realize just done. Logic gate, which means transistors required. Now look at a computer, the number of transistors, millions of transistors. So understanding how one PN junction works, transistor works, how transistors build op amps, how transistors logic gates, how transistors building logic gates that do things like segment is done. Okay, so the working circuit 2 reality, small IC that I showed you, size of that, and you can make your own, realize how electronics evolve and how these are still help you or make you understand the value in an electron. And my pen drive, cell phone, or when you go to a departmental store to buy something working, how an analog value like a weight of the mass of a material converted into that binary value be displayed on a 7. If you want kilograms of rice, shows you 0 kilograms, and that number has gone through development of electronics, be able to convert analog value, so have that value sent across to help you understand and realize it as a human decimal factor, not in hex, not in binary that realize it easily, but form factor. Yes. So if you have any questions, feel free to reach us, and we should be. And let's go to the next topic. That's it for now. So let's review our understanding, our fundamental. Go back to the syllabus. So we did start understanding flip-flops. What is a flip? The ability to work one bit of 0 or 1, on or off, high or low, with about RS flip-flop, reset set flip-flop, D flip-flop, the data in, controlled by the clock. And you saw about the toggle, in other words, an input switch states within high and low, JK flip-flop, where you have two inputs J and K, and your outputs, inverted output and non-inverted output. So the master slave flip-flop, where they cascaded together, and you saw with JK flip-flop, You saw the clocked flip-flop. In other words, the clock has a leading edge trigger and or the level trigger. In other words, as long as it's high, trigger state holds, or when it changes from low to high or high to low, we talked about edge triggering. And you saw the application of flip-flops. Now we saw the frequency divider where we saw an application where we talked about the watch. How does it able to tick exactly by 1 second? Talk about 32,768 hertz in your crystal oscillator, divided to 1 second. So about ring counters where you can go all the way counting from zero to a particular number and back to zero. For example, I want to count to 12 and give me an output when it's 12. I can count to 12 and come back to zero. You saw an application with a 3-bit counter. We saw about counting to 3 and back to 0 with an LED driver board. And you saw shift registers, how it can be used in memory. So a 7-segment driver circuit board. And the rest of the topics we will see it as a separate video. And that would be talking about how data is being handled, coders, decoders. That's it for now. Have a great